In this video, we are going to cover the remaining section from dimensional analysis. So we are going to look into a different way of determining the pi terms, which is called by inspection. We are going to have a look to some of the most common dimensionless numbers in fluid in mechanics, and also the correlation of experimental data and modeling and similitude. So that will be 7.8. Okay, so let's start by reviewing some of the most important dimensionless numbers in fluid mechanics. So the most important probably it is the Reynolds number. So we have the Reynolds number that it is described with RE. It is the relationship in between inertial forces and viscous forces. So when it's important, it's always important. Reynolds numbers is, for most of the cases, is going to be important. Another number is the Mach number. Usually we have it like M or MA. The Mach number, it is the flow speed divided by the speed of sound in the media that we are. So if we have, for example, that the velocity it is supersonic, so that means that Mach number it is bigger than 1. Subsonic will be less than 1, and if we are in the limit, so that will be transonic, so with Mach number is equal to 1. So this is important to consider if the flow is compressible. So we could probably look into the Mach number, and if the Mach number is closer to 1, so we should probably consider compressible flow. Another important number is the Freud number. So Freud number is very important for free surfaces. So free surfaces means the canals, also means the flow in certain types of turbines. That is free surface, is not confined. So and in general it is going to be related with water and bodies floating. For example, for a boat is going to be important the Freud number. Another number it is the Weber number. So Weber number it is the relationship in between inertial forces and surface tension forces. So if we are considering like the examples of where you have the insect standing on the water, or we have the capillarity effect, so Weber number is going to be an important one. Okay, we also have Euler-Boyle number. So Euler number, which is in generally written as CA, it is related with the cavitation. So it is going to tell us how close to the cavitation we are. So it is a comparison of the fluid with respect to the vapor pressure. So remember, vapor pressure it is a very low pressure, and P it is the actual pressure, and they have to be absolute pressures. So it is comparing the pressure, the delta pressure, so how close are we from the cavitation pressure, and inertial forces. So that's the cavitation number. So it is very important if we are considering like the design of a pump, or we are considering any hydraulic machine, or if we are, even if we are considering just the flow around a blade. So we always have to compute the cavitation number to see if we are closer to cavitation. Finally, Strudel number. Strudel number is the relationship in between oscillation and inertial forces. So if the flow is oscillatory, so we should probably take it into account. So these are some of the most important numbers in fluid mechanics. This is an example of computing the pi numbers using an alternative method. The method is called by inspection. So this example is basically resembling the flow through the arteries in the human body. So if this represents an artery, so at some point we have the heart, and so this is somehow connected with the heart. The heart it is a pump, a positive displacement pump. The main difference is that it is going to be working by pulses. So C in our case is going to be the velocity of the blood, and so we are going to have pressures pulses that travel through the arteries. Okay, this is like a web, and we are supposing that this is going to be a function of the artery diameter, the wall thickness, the density of the blood, the modulus of elasticity of the artery, so that the artery is something like elastic, is not a very rigid pipe. And so we want to determine the pi numbers, so we can do some set of experiments. Okay, so let's write the functional relationship. So our relational will be the velocity is going to be a function of the diameter, the thickness of the wall, the density of the blood, and the elasticity modulus of the artery. So from here we have that K, it is going to be equal to 1, 2, 3, 4, 5. K, it is going to be equal to 5, and we need to find out what are the reference dimensions. So let's do our table. So we have C, D, H, rho, and E, and so the dimensions are going to be, let's do our table. So in the first case we have velocity, so velocity it is length per unit time, diameter which is length, thickness which is length, mass, density which is mass per volume, so L cube, and elasticity modulus which is mass divided by length and time squared. So we can see here that we only have length, time, and mass. So R in this case it is going to be equal to 3, so therefore we have K minus 3 minus R equal to 5 minus 3 equal to 2 pi numbers. So we are going to have a relationship which is going to be pi 1 as a function of another function of pi 2. So it's not the same relationship, it's a different one, and so the most important thing here is to find pi 1 and pi 2 in order to do the experiment. So this method is called by inspection. So let me make a line, let's move it a little bit. So okay, so by inspection, so first of all we are going to start with the dependent variable, so that's the opposite to the method before. Now we start with the dependent variable. Okay, so dependent variable it is C, and the dimensions are L over T, length over time. So we need to convert this to into a dimensionless variable. So if we look to the original set of equations that we have here, so we can see that the only one with time, it is going to be elasticity. So and the elasticity modulus have time in the denominator and it is squared. So we need to square root E, and in fact we need to, because it's in the denominator and also in C is in the denominator, so we need to divide C by the square root of E in order to cancel T. So we have to divide by square root of e to cancel t. So let's do it. So we have c divided by the square root of e, whose dimensions are, okay, the original ones, and now we are going to divide by e, so we are going to divide by m lt square, and we are going to, this is the square root of this one, so the square root of this one, so time, it is going to be cancelled, time is going to be cancelled, and then we have length to the power of 1 multiplied by length to the power of 1/2, so that's going to be 1.5. So we have length to the 1 plus a half, it is 3/2. So to the 3/2, and mass, it is going to be to the 1/2. Okay, now we have length and mass, so we need to cancel mass. So if we look in our table, the only one with mass is density, and it's in the numerator, the mass, so we have to multiply by rho, but in reality we have to multiply by the square root of rho because we need mass to the 1/2. So we have to multiply by the square root of rho to cancel m. So we have our previous result, so we multiply by the square root of rho, and the dimensions are, so we have L to the 3/2, m to the 1/2, and multiply by density to the 1/2, so mass to the 1/2, and divided by length cube to the 1/2, so 3/2. So we are very lucky here because we can see that everything cancels. So the dimensions so are none. So this is dimensionless. So we got our first dimensionless number. So from here we can conclude that pi 1, it is equal to c multiplied by the square root of rho divided by e. So we should proceed in the same way and with the rest of the variables that we have. So we already, so for pi 2, we need to involve them and the variables that are left. So let's have a look to, so we already use rho, e, and we already use c. So we have d and we have h, and both are length. So we can very easily form our dimensionless quantity here. So we have that, that's straightforward because both have the same magnitude dimension. So that pi 2, it is going to be equal to d, either d over h or h over d. So pi 2, it is going to be equal to, let's say, h over d. We use the two one that were left. So our relationship will be, this original one will be pi 1, which is c multiplied by the square root of rho divided by e. So everything should be under the square root, equal to a function of h over d. So our new variables are these two. Okay, so in this case it is a little bit easier to deal by inspection. So you can choose any of the methods as far as you can get to the similar results. Okay, let's continue. So our new topic here, it is modeling and similitude. So we can see that we want probably to make a big plane, but we like to know what is going to happen if we build a plane with certain dimensions. We will need to prove the power and a lot of things, and it will be very expensive if we just have to actually build the prototype and see how it behaves, and if it doesn't behave, so produce another prototype. That's probably not going to work. So what we do, it is we use scale models. So we have probably a wind tunnel, and we have a scale model like the one in the picture. So we can measure things and we can compare the results and see what is expected in a real situation. So in a way, experiments and mathematical models are more or less the same. So we want to predict what is going to happen to the real design when we are working on a model. So in this case, the model is a physical model. In the case of a mathematical model, would be an equation that will resemble the real live prototype. So our main statement in this case will be that the flow conditions for a test model are completely similar, so the keyword here is similar, to those of the prototype, to the real thing, if the values of the corresponding model and prototype match for all dimensionless parameters. So that means that all the dimensionless numbers match in the model and the prototype. So if we have a relationship like this one, so we have pi1 equal to a function of pi2 to pi k. So we have pi numbers. So they are similar if all the pi numbers are the same in the model and the prototype. So let's say, for example, we have Reynolds and we have force coefficient. So to be similar, the Reynolds number has to be equal in both cases, and the force coefficient has to be also equal. So in that case, we can compare the results, and that's the way that we can actually predict what is going to happen. And to be fully similar, it has to be true for all pi numbers. However, in real life situations, sometimes it's going to be hard to be equal to all pi numbers. So we want to find out what are the most important pi numbers that are going to be involved in our experiment and prototype. Okay, so what is the prediction that we can do? So we have k pi numbers. So we have this functional relationship, pi1 equal to a function to pi2 to pi k. And so if all these pi numbers are equal in the model and the prototype, so pi2 in the model equal to pi2 in the prototype, pi3 in the model equal to pi3 in the prototype, and so forth until the last one. So if all of them are equal, then the first one should be equal. So we are comparing from 2 to k, and then the first one, that should be equal. So we can gather information. So when we compare, for example, a model airplane and in real life and in the wind tunnel, so what it means that if we double the size, probably the velocity, it wouldn't double. So the rules that are going to govern that relationship between model and prototypes are the pi numbers, similarity in the pi numbers. So we have to look in the pi numbers. We cannot just assume that because we doubled some parameter, everything is going to double. Okay. Okay, let's continue. Well, this is an open question, so probably you should stop here the video and answer the question, and then compare with the result that I'm going to say after. Okay, so what is the answer from this? So the answer is D. Okay, Reynolds numbers represent a relationship in between inertial forces given by rho VL, because this is, remember, rho, it is mass per unit volume multiplied by velocity. So mass times velocity is momentum, so this is inertia, multiplied by L, so that's one representative length, and divided by the viscosity. Okay, viscosity will produce shear forces, viscous forces. So remember, Reynolds number represents the ratio in between inertial and viscous forces. Okay, let's jump into an example of similarity. And this example is on purpose in a different engineering application. So it is more into bioengineering. So basically, or biology, you can say. So we have a copiopod or copiopod, depending. So it is a very small animal. It's an aquatic crustacean. So its dimensions are more or less 1 millimeter. And so what is like to be an animal of 1 millimeter and like being in a fluid like of water or glycerin or whatever it is he lives. So what we want to find out it is what is the equivalent force that is needed to move this kind of animal. But the problem here in this is that we can have the animal, we can see it, but how do you apply a force in this case? It is a very tiny thing. So you probably would like to do a scale model, but in this case the scale model is not a smaller one, it is going to be a bigger one. So we are going to have a 101 scale model, and in that big model, so we are going to apply a force of 1.3 newtons, and then we measure how fast it moves, and we notice that in our model it will move to 30 centimeters per second. That's the velocity. And also we choose a different medium, we choose glycerin medium. So what we want to know it is what will be the equivalent force for the copiopod that is moving in water. Okay, so first of all we have this little table. In this little table we have the prototype and model properties. So we have the viscosity and we have the density for water and for glycerin. Okay, so first of all, so let's start to look into our functional relationship. So we have that the force, it is a function of mu, rho, what else do you think? These are properties of the fluid, but also the velocity, probably faster you move, the stronger the force you need, and the length. So that's probably the most important parameters. And we already did this relationship, and in this relationship it is like the relationship for drag, for a drag force, for a and so we know that the most important parameters in this case, so we have 1, 2, 3, 4, 5, and then the reference dimension were 3, mass, velocity, and time. So the pi numbers were 2, and the pi numbers were Reynolds. which is equal to rho VL over mu, and the force coefficient, which is the force divided by rho V square L square. Okay, so our relationship will be Reynolds in the relationship will be the force coefficient is equal to a function of Reynolds. Okay, so to be similar, what we need it is that the Reynolds in the model be equal to the Reynolds in the prototype. So that is rho VL divided by mu in the model equal to rho VL divided by mu in the prototype. Okay, so let's see what we have. So for the model it is the big scale that we construct. So we know that is going to be water, so we know the properties of the water, density and viscosity. We know the velocity is going to be 30 centimeters per second, and we know the length. Well, the length it is going to be 100 millimeters because it's a 100 scale. And so for the prototype we know the media, which is water. So the medium before was glycerin, to be clear. And so we know the properties, viscosity and density. We know the length because it's 1 millimeters. So the only unknown here is going to be the velocity. So let's try to solve for the velocity. So we have Reynolds in the model, this computer Reynolds in the model. So we have density, which is for the glycerin 1263 multiplied by the velocity, which is 0.3 meters per second, multiplied by the length, which is 0.1, and this is going to be divided, and the viscosity of the model, which is 1.5, and so this is going to be 25.26. So this is clearly laminar. And for the prototype, Reynolds of the prototype, so what we have it is density it is 999 multiplied by the velocity in the prototype, we don't know the velocity, multiplied by the length, which is 1 millimeter, and divided by the viscosity, which is 0.001. So from here we have that Reynolds in the model is equal to the Reynolds of the prototype. So we can solve for the velocity. So we have 25.26 multiplied by 0.001 divided by 999 and divided by 0.001, and that should give us a value of 2.53 10 to the minus 2 meters per second. So that's the velocity in the prototype. So it's very tiny velocity to be measured, but via the experiment, the scale experiment, we can be able to tell. So we have the equivalent velocity. So we would like to know what is the equivalent force that we want to produce. So we were comparing here Reynolds, but we have another pi number, which is the force coefficient. So we have that the force coefficient for the model should be equal to the force coefficient for the prototype. Now the force coefficient for the model it is force divided by rho v square L square divided, this is for the model. And so we have the force in the model. We know the force in the model, we know the density in the model, the velocity and the length. So this is basically force of 1.3 newtons divided by 1263, which is the density, multiplied by the velocity. We just find out, no, the velocity was given was 0.3 square, and the length, which is 10 centimeter square. So this will give us a value of 1.14. Now, because this is equal to the force, the coefficient of the force coefficient of the prototype, and the force coefficient of the prototype is F in the prototype divided by rho in the prototype, velocity square in the prototype, and length square in the prototype. So let me, and so this is it. So force in the prototype, it is not known, but apart from that, the density, which is 999, the velocity, which is 2.53 10 to the minus 2 square, and the length, which is 0.001 square. Okay, so from here we can solve for the force in the prototype, equating these two. So this is 1.14 multiplied by 999 multiplied by 2.55 10 to the negative 2 square, and multiplied by 0.001 square. This is the force in the prototype. And so if we input this in the calculator, we are going to have a force of 7.31 10 to the negative 7 newtons. So this is a very tiny force to be measured. So you can see from this example the advantages of having a similarity.